Dah, dah.
Okay. Mungkin nak share slide dulu ke? Oh. Okay. Bersama-sama kita adalah Cik Nurul Amira Sakinah binti Abdul Jamal. Beliau merupakan student master di Muasalian Profesor Muhammad Rizal. Dan hari ini beliau akan membentangkan kajian bertajuk New Identified Strategies for Forge Multivariate Signature Schemes. Tanpa memegang masa, saya serahkan ruang ini kepada Cik Nurul. Dengan selamatnya disilakan.
Okay, terima kasih Dr. Rohizat. Okay, Assalamualaikum and good afternoon to all lecturers, staff and students. My name is Nurul Amira Sakinah binti Abdul Jamal. I am master student of mathematical cryptography at Inspem under the supervision of Professor Dr. Muhammad Rezat. So today I would like to share my research findings through this weekly seminar, and the title is New Identified Strategies to Forge Multivariate Signature Schemes. So the author is me, Professor Dr. Muhammad Rezal, Associate Professor Dr. Siti Hasanah Safar, and Miss Kamila Abdul. This paper was published on 10 November 2022 in Symmetry. So this is an insight to our research. A road certificate authority or RCA is a dishonest entity that has the trust of web browsers and users to produce valid key pairs which are vulnerable. This work analyzes two acknowledged post-quantum secure multivariate quadratic problem or MQP based signature schemes, namely the UOV and rainbow signature schemes that obtain their key pair from a potential RCA methodology. We revisit two and provide a novel RCA methodology that would enable adversaries to forge UOV and rainbow signatures. We also lay out two strategies to identify whether the public parameters are elusive. As such, the UOV and rainbow schemes remain vulnerable to forgery if it was forged via the third methodology. So our research focuses on multivariate signature schemes, UOV, rainbow, MQP, RCA, weak public key, and post-quantum cryptography. Firstly, I would like to introduce the basic terms related to this paper. Symmetric key cryptography uses the same key to encrypt and decrypt, where asymmetric key cryptography, the decryption key is different from encryption key. Next, we should know that digital signature provides data integrity and authenticity, disallow repudiation, and the private key is used to sign, public key is used to verify. Certificate authority is an entity who is responsible for generating the key pair, where back certificate authority could be among the CAs trying to induce the weaknesses into the key. The weaknesses are only known to RCA. So MQP or multivariate quadratic problem is the hard problem in multivariate public key crypto system, MPKC. It is a problem of finding a vector X such that when we substitute X into the polynomial system P, all equals to 0 modulo Q. Given that P is a system of M equations in N variables under finite field Q with Q elements. So in multivariate cryptography, UOV and rainbow are among the strongest crypto system for digital signing. In UOV, we have the so-called vinegar variables and oil variables, where vinegar variables are the first V variables and the rest are oil variables. There are only two secret keys in UOV scheme, which is F and T. F is uh, F is central map, which is also a quadratic polynomials, and T is linear maps in matrix form. To generate a sign for document D, we need to hash D first. Then we choose V random values and substitute into F, and we use Gauss elimination to solve for oil variables. The signature is set computed like this, and to verify, we just need to compare the H of D, which is W, with the computed W prime, which is equals to PZ. Rainbow signature scheme is an advanced version of UOV. It has multiple layers of UOV with smaller signatures and key size. Observe that the form of central map F is a bit different from UOV, as the polynomials in F have different lengths. This is because the index A and B of variable X depends on PL and OL. So the private key consists of S, F, and T, where the public key is computed as P equals to SFT. The signature generation for Rainbow is quite similar to UOV. As we can see here, we have to substitute random values into F to solve for. We have to substitute random values into F to solve for oil variables, but this process is done layer by layer, from layer 1 until layer U. Now we will take a quick look on theorem and lemma from this research paper, as the research we are discussing now is an extended version from that paper. So theorem 3.1 states that if the constants of polynomial system P can be written into this form, which is multiples to each other, so we only have to solve one polynomials to solve the whole system. And lemma 3.3 states that if we have a solution for F1 until Fm, so we can solve for Fh, which is the summation of F1 until Fm. Algorithm 2 and 3 were also presented in previous papers. Algorithm 2 describes a forgery mechanism based on theorem 3.1, where it applies the MQP structure on central map F. This would result P with the similar structure. And algorithm 3 is to identify DSFM1 to identify this type of forgery. One need to compute for K as in step 2, where CPJ and CP1 inverse are the coefficients of polynomials Pj and P1. If Kj satisfy the structure, then we declare P is a forgeable system. In this research, we try to implement DSFM1 into UOV. This can be done easily by setting the polynomials in map F into the structure. And finally, the computed P will also have the similar form. To avoid verification failure, the vector for W, the H for D, must also be in multiples of each vector W. An adversary who wants to forge a signature just have to solve for P1 or any other Pi in the system P, and he can solve the whole system and generate a valid forged signature. This forgery is based on theorem 3.1, and we can directly use algorithm 3 to identify a weakened DSFM1 UOV scheme. DSFM2 is based on lemma 3.3, where the private key S is 2 by 2 matrix, T is n by n matrix, and F is 2 polynomials in n equations. After computing for determine the random value for P1 and P2, we generate P3 until Pm by adding the previous polynomials. For example, we have P1, P2. We compute for P3 equals to P1 plus P2, and P4 equals to either P1 plus P2 or P1 plus P3 and so on. Algorithm 5 is used to identify the SFM2. We only have to check if Pi plus Pk equals to Pj is true. For J from 3 until M. In this research, we try to implement the SFM2 into UOV. In the second step, you only have to choose 2 initial polynomials that satisfy the criteria for central map F in UOV, and compute for F3 until Fm using this formula. The structures for polynomials in P will also satisfy this condition. To avoid verification failure, the vectors in W must be the summation of each other, since the polynomials in system P and F are also in the similar form. If adversary already knows that the key pairs are generated from a weakened UOV scheme, he just has to solve any Pi and Pk such that Pj equals to Pi plus Pk to solve the whole system and successfully generate a forged signature. And algorithm 5 can be used directly to identify a weakened DSFM2 UOV scheme. So what we just discussed so far, the forgery strategies were only applied on UOV. Now we will take a look on why rainbow scheme is safe against the SFM1 and the SFM2. For the center map F of UOV, every polynomial layers have the same structure. Observe that for K from 1 until O, the index for variable X are from V or O. So when we do addition or constant multiplication, the structures of all the resulting polynomials remain the same. If we observe the central map of rainbow, the index A and B of variable X for all terms depends on the VL and OL. So for every S layer, the polynomial structures are not consistent. If we do constant multiplication and summation of 2 polynomials, it will not generate a central map that satisfy this condition. This means every layer will have the same structure like UOV, so we cannot apply DSFM1 and DSFM2 in to rainbow. DSFM3 is our proposed forgery strategy that was published in Symmetry. It is a way to forge signatures without having to alter the construction of public key or even the secret keys. Assume that the adversary successfully solicits X from RCA. This means Px equals to 0. And let alpha be an unknown. We substitute X plus alpha into P. And the system is transformed from polynomials with m equations in n variables into a system of m equations in only one variable, that is alpha. Then we solve for alpha. We produce a valid signature, that is x plus alpha is the signature. So we z prime substitute into p, we get the vector W, which is the hash for the document. For example, suppose that this is the vector solution for P obtained from RCA. Z is the original signature from the sender, and W is the hash for the document. We have P1, P2, and P3, the polynomials in system P. So the adversary computes Px plus alpha and obtain this equation, and solve equals to W1, P1 equals to W1, P2 equals to W2, and P3 equals to W3, and obtain the value for alpha equals to 23. So we add the value of alpha into the the vector solution X, and we get Z prime. This is the valid forged signature, which outputs the value of hash of the documents. So in conclusion, we have revisited two signature forgery methodologies, DSFM1 and DSFM2, and put forward one novel signature forgery methodology, which is DSFM3. The public key system P of a UOV signature scheme is not secure if it is generated using the SFM1, 2, and 3 methodologies by RCA. Potential users of UOV scheme are able to identify whether the public parameters are generated via the SFM1 and 2 methodologies. As such, they must conduct due diligence upon receiving the public key system P. To this end, the rainbow signature scheme is resistant to DSFM1 as well as DSFM2 methodologies, and is only vulnerable to DSFM3 methodology. However, it is still an open question whether a public key system P of UOV and rainbow schemes can be identified if it is generated via DSFM3 methodology, since there are no anomalies in the public key. That's all from me.
Terima kasih. Betul di atas pembentaran. Mungkin kesempatan ni saya buka soal jawab sekiranya ada persoalan ataupun pertanyaan daripada situ. Sekiranya ada soalan lah, okey. Teruskan Dr. Ashraf. Ada soalan.
Ya, Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum.
Thanks Amira for the great presentations. Boleh dengar suara saya?
Dengar.
I just want to have some explanation. Do you know that you are discussing about UOV and rainbow, right?
Apa dia?
Sekarang discuss UOV and rainbow kan? And then we have research, we have result that there is a key recovery attacks. So actually the actual attack to rainbow lah.
There is a key
Key recovery attacks. So sekarang ni yang this one is not attack kan? This is not boleh break the rainbow, betul? Okay, so apa pandangan awak exercise untuk mengenal pasti kemungkinan forgery, tetapi telah ada kaedah untuk attacks, which is practical to have a key recovery attacks. Maksudnya dah ada attack yang berjaya untuk break rainbow, tapi research ni adalah seolah macam backward lah, iaitu kita just ambil weak sample of rainbows. Tu boleh minta explain sikit.
Personally, I think that key recovery attack tu quite complicated to solve. And my proposed method is very simple.
Kau kan masa key recovery attack tu dah berjaya attacks. Yang ni bukan attack kan?
Ini bukan attack private key, bukan nak recover private key. We just want to produce a valid signature based on public key only.
So I want to get a clearer picture lah about this exercise. Apakah keperluan untuk kita dapatkan forgery jika sistem tersebut boleh kita dapatkan dia punya secret key? Faham ke dia punya situasi? Saya nak make it clear lah maksudnya.
Boleh mencelah lah. Maybe I can ask a related question lah. Can the forge certificate or forge signature yang kamu tunjukkan tadi boleh diserang melalui key recovery attack?
Kau bukan
boleh.
Kau kan dia bukan boleh diserang. Apakah exercise ini ada keperluan, iaitu kita dah ada satu serangan yang boleh dapatkan key.
Yalah, faham. Tapi mungkin dia punya force signature ni tak boleh kena attack dengan key recovery. So still valid result lah kalau tak boleh lah, kalau tak boleh.
Key recovery dah dapat key, kenapa nak force kan? Maybe there's some clear explanation.
Maybe kalau dah ada method untuk atasi key recovery attack tu, kan dia UOV dengan Rainbow kan kadang-kadang dia buat modified version untuk stop attack tu. So bila dah berjaya modified UOV dengan Rainbow tu, tapi still vulnerable against this proposed attack. Because kalau DSFM3 ni dengan yang lain pun dia based on public key.
So your proposed scheme is also applicable on the modified version of Rainbow and UOV. Is it correct?
Might be. Saya tak check lagi lah kalau, sebab saya pun tak baca pasal key recovery attack tu. So kalau mungkin lah kalau ada apa ni, ada method untuk halang key recovery attack tu.
Just to add up for your preparing the literature review, updating the literature review. This is because Rainbow is now being pushed away from candidate kan, NIST. So ada queries lah kat sini about this. That's the result is the result. No, tak perlu fikir pasal ni. Yes. Saya nak tengok distinction between an actual attack and forgery. Adakah keperluan untuk buat dua beza ataupun ini benda yang sama.
I have another question. Is there any difference in terms of key size between the forged signature and the actual signature?
No, because everything we did is based on modulo Q.
So kalau yang actual signature dia modulo Q juga.
Semua computation ni kita buat dalam modulo Q.
So no difference in terms of key size lah. How about the signature size? Pun sama juga modulo Q.
Signature size. Semua.
So all of the parameters are in modulo Q.
Yeah.
I mean, your method. This is my opinion lah. I don't know whether you can check after this or not. I think you can extend your method to become what we call as a key escrow system. Do you familiar with the key escrow system?
Actually mula-mula buat bawah topik key escrow. Tapi dia tak satisfy konsep.
Konsep apa ya?
Konsep key escrow. Bila baca balik. So tukar kepada forgery.
Oh, okay. Alright. Okay, thank you.
Okay, thank you.
Okay. Terima kasih Dr. Amir dan Dr. Ashraf. Mungkin ada lagi soalan ataupun komen?
Nak tanya, is there any example in your paper?
Ada.
Alright.
Tu ada example.
Ada. Okay, alright. I will refer to your paper later.
Okay, thank you.
Amira, yang ini signing kan, UOV dengan Rainbow ada encryption tak?
Tak, UOV dengan Rainbow memang signature scheme je.
Saja
Ya.
Okay.
Okay, terima kasih Prof. Mungkin ada lagi soalan atau mungkin dah tak ada soalan. Saya ucapkan terima kasih kepada Encik Nur Amira di atas perkongsian, dan mungkin sesiapa yang mungkin nak bertanya lebih lanjut mungkin boleh terus kontak dengan Cik Amira. Dan terima kasih juga pada semua yang menunggu hingga ke saat akhir ini, dan saya lagi ucapkan terima kasih dan selamat berpuasa dan selamat menunggu untuk berpuasa lah. Dan kita jumpa lagi pada sesi akan datang. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Terima kasih Doktor.